Okay, so hello everyone again. This is lecture number 2 on motion in a straight line. So in this lecture, we will start with the fundamental discussions about your average speed, average velocity, etc. In the previous discussion, that was the first lecture on motion in a straight line. We completed our discussions about what is basically the path length, what is basically your next concepts regarding displacements, etc. What was the difference between your path length and your displacement were all being considered here. Now, in this lecture, we will start with the next discussion that is based upon your average speed and average velocity. Okay, so let's start the discussion directly. Let's not waste any time. So, I'm Sandeep Lawankar. Let's begin our discussion. Okay, so first of all, let's start with this discussion that is the course outline. So, right now, we are on the third topic. We'll start with the third topic today that is average speed and average velocity and average speed. In the previous discussion, we completed the introduction part of what we are going to understand in this chapter. So we are basically understanding everything which is in a straight line only. So everything in our considerations will be explained using only two sign conventions, that is plus and minus, because if you're only considering one sort of movement, then it can either go in the right hand side or it can go on the left hand side, or either it can go upward or down. So only plus and minus will be required for the motion. Rest all thing will be explained or dealt with when we are trying to increase the dimension. Let's say it is 2 dimension or 3 dimension, etc. Okay, so that thing is also explained. Then the second point, we also understood the basic difference. So what is basically path length, what is displacement. So please remember, displacement can be zero also, it can be equal to path length also, it can be less than path length also, but displacement cannot be greater than the path length. Path length can be greater than displacement, but displacement cannot be greater than path length. Okay, that being said, let's start today's discussion that is based upon your average velocity and average speed. Okay, so let's start. So when an object is in motion, its position changes with time. But how fast is the position changing with time and in what direction? So to describe this, we define the quantity that is average velocity. Okay, so what is basically average velocity? It is nothing but your change in the displacement, that is x2 minus x1 upon t2 minus t1. So that is the basic crux of average velocity. Okay, please remember here the numerator part is your displacement. Okay, it's not the path length, it's your displacement. Okay, so average velocity is defined as the change in position or displacement delta x divided by time delta t in which the displacement occurs. Therefore, average is basically this value, that is v bar, which is equal to x2 minus x1 upon t2 minus t1, which is equal to delta x upon delta t. Okay, so here the bar over the symbol for velocity, as you can read up here also. So here the bar over the symbol for velocity is a standard notation used to indicate an average quantity. Okay, please remember. So this is a formula. First of all, the first formula which is arrived, that is v bar, which is equal to x2 minus x1 upon t2 minus t1. Okay. Please remember the SI unit of velocity. SI unit of velocity is meter per second. Why? Because delta x is in meters, delta t is in seconds. So that is basically meter per second. Okay, we can also write this as equal to nothing but meter second inverse. Okay, that is also explained. Next thing is, like displacement, average velocity is also a vector quantity. In the previous discussion also, we understood this thing came into picture as in what is vector quantity. So please remember that displacement, like displacement, the average velocity is also a vector quantity. But as I explained earlier, for motion in a straight line, the directional aspect of the vector can be taken care only by plus and minus sign. This is only and only because we are taking the simplest case here, that is of motion in a straight line or motion along, let's say, one direction. For our case, it's x-axis. Okay, so it can be taken, and the directional aspect of the vector can be taken by plus and minus signs, and we do not have to use the vector notation for velocity in this chapter. Okay, then we will just move on to the next chapter about motion in a plane. Then there will be need for understanding the vector quantities, vector displacements, vector and addition of vector, etc. in much detail, which will be clear that complete chapter, the most proportion of that chapter is based upon understanding of vectors. Okay, so please don't be hesitant. You will understand each and every concept clearly as we move. Fine. So now let us consider the motion of the car as shown in the figure above. Okay, so let us try to understand the motion of the car here, what is actually happening, and then we can try to understand what is the average velocity here in each of these scenarios. Okay. So the portion of the xt graph between t is equal to 0 seconds to t is equal to 8 seconds is blown up as shown in the figure below. So this is basically magnified here as you can see. Okay, so as seen from the plot, the average velocity of the car between time t is equal to 5 seconds and t is equal to 7 seconds is. How to find out the value? We know the formula. What is v bar? V bar is nothing but equal to x2 minus x1 upon t2 minus t1. Please remember every time the first value, that is x2 or t2, is the final value, and the after minus sign the next value is the initial value. Okay, so if I just even write it like this, let us write it more generally. So v bar is nothing but equal to x final minus x initial upon t final minus t initial. Okay, so that is how it can be understood. So therefore, as seen from the plot, at t is equal to 5 seconds, 5 seconds would have been somewhere here, 7 seconds would have been somewhere here. So they have just magnified this thing here. So we can actually find that at t is equal to 5 seconds, the displacement was 10, and at t is equal to 7 seconds, the displacement was 27.4. Okay, so just putting those values here, you will get the average velocity is equal to 27.4 minus 10 upon 7 minus 5, that is equal to 8.7 meter per second. Okay, geometrically this is the slope of the straight line. Okay, so slope maybe a new concept or new word for you. So slope is nothing but, for now you can understand this as tangent of the graph. Okay, so basically what is slope? So slope is basically the angle, this. So this is called as slope actually. So how to calculate the slope? We can basically find a tangent of this triangle or tan theta of this triangle and found out this slope. Okay, so as you keep on moving on, this tangent will be, this slope will be a very peculiar concept, very easy concept, because it will be used in each of the concepts you will understand in the later part. Okay, so we can understand that delta x2 minus x1. So basically what we're trying to find, out the slope. Okay, so the slope is basically, you can understand from this portion. So there is a slope of the straight line p1 p2. So we are trying to find out the tangent of this straight line p1 p2, connecting the initial position p1 to the final position p2 as shown in the figure. Next thing, the average velocity can be positive or negative depending on the sign of the displacement. Quite evident. Let us write this again. So it's nothing but x2 minus x1 upon t2 minus t1. Right? So let us say that if x2 is less than x1, that simply means that x2 minus x1 will be negative. Right? If x2 minus x1 is negative, then it is surely that v bar will be negative. And if x2 is greater than x1, then x2 minus x1 will be positive, and hence v bar will be greater than 0. Hence, what we understood from this is that the average velocity can be either positive or negative depending upon the sign of the displacement. Quite evident. So if the sign of the displacement is positive, then this will be positive. If it is negative, then this will be negative. Okay. Fine. So it is 0, the displacement is 0, quite evident. If the delta x value is 0 or x2 minus x1 is 0, then the then the velocity will always also be 0. Let's move on then. The next figure shows you the xt graphs for an object moving with positive velocity. As you can see, positive velocity, how can we say? Because the slope of this graph is positive. Okay, so either we can directly look at the graph. If it is going upwards, then the slope is positive, or what we can say, the tan theta is positive. Right, so if tan theta is positive, then we can say that the slope is positive. Next thing is moving with negative velocity. As you can see, it's going downward, so it is having a negative velocity. And because here the slope is 0, as it is slope is 0, so we can say that it is at rest. And also one thing also can be understood from this, or can be read from this. As you can see, for each of these time periods, right? Let us take any time. Let us take this time. Let us take this time. You can see the value of x is constant. Right, so x2 and x1 will be same. If x2 and x1 is same, then x2 minus x1 will be 0. If it is 0, then the slope is 0, or the average velocity is 0. Average velocity is nothing but the slope of the position time graph. This is called as a position time graph. Okay, so any graph which is drawn between y-axis as x and x-axis as t is called as a position time graph. Okay, position time graph. Okay, fine. Let's move forward then. So figure shows the xt graph for an object moving with positive velocity, figure A, moving with negative velocity, figure B, and moving and at rest with figure C. Okay. Average velocity, let's move to the next point. So next point states that average velocity as defined above involves only the displacement of the object. Okay, so the displacement of the object is happening, then there is change in the average velocity number or average velocity calculation. Okay, we have seen earlier that the magnitude of the displacement may be different from the actual path length. It is very, very evident, right? We have understood one concept in which, let us say, this is the straight line which we are working upon, right? Let's say this is the origin O. Now, if we go in this direction, then come back, go in this direction, then again come back, and let us say go in this direction, the total path will be covered in this. Will add this to it, and this will add this to it. But actually, the displacement would be what? This will be only this much. Okay. This is your displacement and this is your total path length. Okay, so we have already understood that in the first lecture of this chapter. Moving on, so we have seen that earlier that the magnitude of displacement may be different from the actual path length, quite clear. To describe the rate of motion over the actual path, we introduce another quantity called as average speed. Okay, so quite evident. We can also write the formula for average speed. What is average speed basically then? Average speed is nothing but total distance covered, or we can write it as total path length covered. Total path length covered upon total time, right? Similarly, what we can write for average velocity? What is average velocity? Average velocity can be defined as average velocity is nothing but total displacement upon total time taken. Okay, so that is how you can define average velocity and average speed concepts. Okay, so to describe the rate of motion over the actual path, we introduce another quantity called as average speed. What is average speed? The definition of average speed is written here for your reference. So average speed is defined as the total path length traveled divided by the total time interval during which the motion is taken. Therefore, average speed will be a total path length upon total time interval. So that is only the definition they just gave you. So it is just thing, but mathematical form is this and the written form is just about it. Okay. So that is the definition of your average velocity and average speed. Hope it is clear to you. Let's move on. Okay. So average speed has obviously the same unit as that of velocity. Why? Because it is some path. As you know, path is the path upon time, right? Path is measured in, let's say, meters and time is measured in seconds. Therefore, the unit here will also be meter per second. Okay, but please remember that displacement average speed is a different concept. Average velocity is a different concept. Okay, next point, but it does not tell us in what direction an object is moving. Very, very important, because it does not tell. Why it does not tell? Because path length is always a positive value, right? So if it's a positive value only, and let us say that the final position in which we moved was the backward direction. Let's say I'll give you an example to make it quite clear. Let us say this is the point O, this is point P, and this is point R. Let us say we first move in this direction, go till here, then we move backwards, go till here, right? The total path length will be nothing but this length plus this complete length. That will be coming as a positive value, right? So from this value, we cannot understand as in what is the direction of movement of the object. But if you try to calculate displacement, please remember displacement will be final value minus initial value. What is the final value? Negative of something, right? Because it is in this direction. The sign convention says that if we move forward, we take it as positive. If we go backward, we take it as negative. And it will be final minus initial. So as you can see, the displacement will come out to be negative. If the displacement comes out to be negative, the average velocity will come out to be negative. If the average velocity can come out to be negative, we can say yes. So there is a velocity of, let's say, x, any velocity v happening in the negative direction. So that can tell you the magnitude also. That can tell you the what we can say direction also. Okay, so that is the advantage of velocity, average velocity over average speed. Okay. So moving on to the iteration part, so that it is always but it does not tell us in what direction an object is moving, average speed. Thus, it is always positive. In contrast to the average velocity, which can be positive or negative. So I just explained to you. So negative example. Similarly, the positive example can be, let us say that it has moved from O to somewhere which is on the right hand side direction. The final position was somewhere in the right hand side direction. Okay. So if the motion of an object is along a straight line, so if the motion of the object is along a straight line and in the same direction, the magnitude of displacement is equal to total path. Okay, so they are just saying that let us say there was a origin point O and this was the final position A, and when the motion is object along a straight line in the same direction, let us say this is only the motion of the object. Okay, so if this is the motion of the object, the magnitude of displacement is equal to total path length, right? Because total path length will be also x and displacement will also be x, right? Similarly, let us say we are at this O position and we are at this R position. Okay, so if you are moving in this direction, the total path length will be x only, and this one will be minus x. Then magnitude of this will be same. Okay, they are just saying the magnitude of displacement will be same. Magnitude of displacement is equal to total path. Fine. So this thing is also clear. In that case, the magnitude of average velocity is equal to average speed. Please remember, magnitude is always mod of that value, right? The mod of that value, so mod of average velocity will be equal to average speed. That has only been explained. Okay. This is not always the case, as you will see in the following example. Okay. So there will be typical examples into understanding as if something there are some exceptions to the above statement being said. So let's look at this example. Let us try to understand each and every example clearly. This complete chapter owns several examples, and then finally we can move on to kinematics equations. Okay. So kinematic equation is the final topic of this along with the relative velocity. Okay. Fine. So let us look at the question. So a car is moving along a straight line, say OP. So let us say the car is moving along this direction in OP. It moved from O to P in 18 seconds. Fine. So let us say this time was done in 18 seconds. Okay, and returns from P to Q in 6 seconds. So this time was done in 6 seconds. So what are the average velocity and average speed of the car in going from O to P and from O to P to Q and back to Q? Okay, so you just need to calculate the value of average velocity and average speed. Okay, fine. So let us try to calculate everything. What is average velocity? Average velocity is nothing but your displacement value upon total time taken, right? So what is displacement value? Displacement value will be from O to P. The final value is P. Initial value is O. Therefore, this will be final value, that is plus 360 minus 0 upon time taken will be 18. It is given in the question. Therefore, it will be 360 divided by 18. As you can see, that answer came out to be 20 meter per second. Fine. Similarly, let us try to calculate now average speed. So average speed will be, so average speed will be nothing but equal to path length upon total time. So path length will be what? Path length will be same again. So this will be again 360 upon 80. So that will again give you the value which is equal to 20 meter per second. Okay. So for the first case scenario, that is A part here, average velocity is equal to average speed. Okay. That being said, let's move to the next example. Next question says that we need to go from O to P and back to Q. Okay. So this is the complete path length. This plus this. Okay. So let us denote this by 1 and this by 2. Okay. First of all, let us calculate the value of average velocity. So average velocity is nothing but equal to displacement upon time taken. Okay, so displacement is what? Displacement is nothing but equal to final value, that is final Q minus O. What is final value? It's plus 240 minus 0 upon what is total. Please remember it's total time taken. Okay, so total time taken will be 18 plus 6, which will give you 24. Hence the correct answer will be plus 10 meter per second. As you can see, plus will tell you that yes, okay, this is the direction of movement. Okay, so as you can see, plus 10 meter per second is the answer for this. Moving on, let us find out the value of average speed now. What is average speed? So average speed will be nothing but equal to path length upon total time taken. Okay, so what is the path length? Path length will be O to P, which will give you plus 360 plus this value, which is 120. So it will be 360 plus 120 upon 18 plus 6. Okay, because 18 is being required from O to P and 6 is required from P to Q. Therefore, this will be nothing but equal to 20 meter per second. So in this B example, you can see quite clearly that the average velocity is not equal to average speed. Average velocity came out to be 10 meter per second. Average speed came out to be 20 meter per second. Okay, so that being written. So as you can see, you can just refer to this also. We have explained this. I've explained this. So average speed is nothing but equal to magnitude of average velocity. But in this B case, the average speed is not equal to the magnitude of average velocity. Okay. So this happens. Why does it happen? This happens because the motion here involves change in direction, so that the path length is greater than the magnitude of displacement. Okay, so as there was a difference between the magnitude of displacement, time taken was same. As you can see, time taken was same. Only the value which changed was the numerator part. In the first average velocity, we explained it using the displacement. In the uh, average speed, we understood or explained this using using total path length. Okay, so this shows that speed is in general greater than the magnitude of velocity. So please use it as a very star point. You can even remember this. It is just saying that average speed is greater than average velocity, magnitude of average velocity. Okay, we are saying that speed. Let us not write average also here. It's just speed. So as to make it much more clear. Okay, so it's nothing but that speed is greater than magnitude of velocity. Okay, so generally, as you can see here also, that speed was greater than velocity. Okay, why it is the case? Because generally path length is greater than displacement. Okay, so if the car in the example 3.1, the previous example only, moves from O to P and comes back to O in the same time interval, the average speed is 20 meter per second, but the average velocity is zero. Okay, how? So because why will be average velocity zero? Average velocity will be zero because the displacement will be zero. Okay, because displacement will be zero because we're going from O to P and P to O. And if you do this same thing for your average speed, so for average speed, what would happen? Average speed will be equal to 360 plus 360 upon 18 plus 18. That will give you the answer as nothing but 360 into 2 upon 18 into 2. 2 gets cancelled. 18 to 20 is a 360, it's 20 meter per second. This will explain. Okay, so in the example, if the car in example 3.1 moves from O to P and comes back to O in the same time interval, because it is saying it is in the same time interval, that's why I added 18 plus 18. Okay, so that was the reason I added 18 here. So maybe some people may ask why I used 18 again. So it is written that it is in the same time interval, and the average speed is 20 meter per second, but the average velocity is 0. Okay, fine. So that was the complete concept about average velocity and average speed. We understood this concept quite clearly. Also, we understood why was average speed greater than average velocity. We also understood this complete concept using an example also. Fine. So that being said, let's move on to the instantaneous velocity and speed concept. So this may require a bit of calculus, limits, etc. So just try to understand as much as you can. As the days goes by, as you start understanding the mathematics of class 11th, etc., then it will be very, very clear, because in general terms, everything after 11th and 12th class, everything will be in terms of your instantaneous or limits or calculus parts only. So calculus plays a very important role in physics, and that will be utilized. Okay, so let's go with understanding instantaneous velocity and speed. Okay, so let us begin. So the average velocity tells us how fast an object has been moving over a given time interval, but does not tell us how fast it moves at different instants of time during that interval. An example of the first thing which is said, so that you can understand this quite clearly. So it is just saying that, let us say I have a time interval from t is equal to 0 to t is equal to 10 seconds. Fine. How can we calculate the average velocity? Average velocity can be calculated as nothing but equal to final displacement minus initial displacement upon T2 minus T1. Right? Let us say we have some displacement at t is equal to 10, we have some displacement at t is equal to 0, and the denominator will be 10 minus 0. Okay, so that will tell you the velocity with which the object is moving in the complete time interval range. Okay, what if somebody asks, give me the value at t is equal to 4.7 seconds? Right? What will be this value? This value won't be equal to, there are very high chance, there is very high chance that that value won't be equal to average velocity. Okay, because we don't know the value at that portion, right? So there should be a concept which can understand or make us understand that what is the value at the position or at the time which is being asked. How to do that, what is the procedure behind it, what is the application is being understood from this and the subsequent topics which we will understand. Okay, let's start understanding instantaneous velocity and speed. The term, as we already know, instantaneous is at an instant. So at any instant, if it is asked. So let us say this is the complete time range which is given to us, and we need to find out the value at this instant. Or let's say this instant. So that is the basic reason of understanding instantaneous velocity and speed. Okay. So instantaneous velocity and speed. So the average velocity tells us how fast an object has been moving over a given time interval, but does not tells us how fast it moves at different instants of time during the interval. So different instant means, let us say t is equal to 3.1 second, or t is equal to 4.7 second, or t is equal to 7.3 seconds, etc. Okay. For this, we define instantaneous velocity or simple velocity v at an instant t. Okay, so now we are trying to understand what is the instantaneous velocity. The velocity at an instant is defined as the limit of the average velocity as the time interval delta t becomes infinitesimally small. So that is how we denote limit concept. So let us understand again. So basically what is happening, let me try to make you understand as much as I can. Let us say we have some value of delta x and delta. Okay. So what is basically delta x and delta t? Let me use this. That will be much more clear. So what is basically velocity? So what is basically velocity? Velocity is nothing but equal to your x2 minus x1 upon t2 minus t2. Right? Let us take the first case scenario. Let us take case 1, in which we are taking the value of t2 is equal to, let's say, 10 seconds. t1 is equal to 0 seconds. Okay. If this is the case, delta t becomes 10 seconds. Let us take case 2 now. Then here t2, let us take 5 seconds. Let us take t1 as 0 seconds. Here delta t is becoming 5 seconds. Let us take even another case. Let us take case 3, in which your t2 is 1 second and t1 is 0 second. Delta t here becomes 1 second. Right? So as you can see that as I take the cases towards the right hand side, the value of delta t keeps on decreasing. Quite evident. In general terms, you can also say that as I'm trying to decrease the value of delta t, there is a very high chance, let me say there is complete success chance that the displacement will also decrease. Right? The displacement is decreasing, then there will be some value of delta t. Let us try to decrease delta t into very small value. If I take it as very small value, in mathematical terms, I call it as infinitesimally small. Infinitesimally small value. So if I take infinitesimally small value, what happens is the value of delta x also becomes infinitesimally small. So what we can say, let me try to make you understand using this situation. Let us take, we have some graph here. Okay, let us say this is the value of delta t for the first case. Let me take different colors. Okay, so let us say this is the, okay, so that will not be understood then clearly. Fine, wait. How to explain to you? Just give me 1 minute. Okay. So let us take this to be t is equal to 10 seconds, t is equal to 5 seconds, t is equal to 1 second. Okay. So as you can see that if I try to make a slope for this value, it will be somewhat like this. If I try to make a slope for 5 number value, this will be somewhat like this. If I try to make a slope for one value, this would be somewhat like this. Now, if I try to decrease as you can see, the slope is trying to keep aligned to the position of the actual value, which is trying to be at this location, which is what we are defining as instantaneous velocity. To find out the instantaneous velocity, we try to decrease delta t so much small, which is in mathematical terms called as infinitesimally small, so that we can find the slope at this location. In the previous concept of average velocity and average speed, we understood that velocity is nothing but the slope of the position time graph, right? So if we are trying to find out the instantaneous speed, instantaneous velocity, what we will do, we will try to uh, decrease the value of delta t so much small such that we will find just that instant of displacement, so that we can find that what happens to the velocity at that complete instant or at that instant. So if we try to decrease, we will get that slope, and that is how we understand the concept of this instantaneous velocity. So hope I was able to explain to you basically why we are doing all these concepts. So if you can also say that if the amount of delta t is very high, it cannot tell you the exact with exact clarity what is the slope at a particular location. To get the slope at a particular location, you need to decrease the value of delta t to a very small extent. And that is a complete procedure, that is a complete methodology which is adopted here, so that we can get the instantaneous velocity or instantaneous speed. Okay, so hope it is quite clear. As the days progresses, as you try to understand physics at a clear depth, these all things are very basics. Okay, fine. So let us understand clearly afterwards. So this thing is explained. So now, the velocity at an instant is defined as the limit of the average velocity as the time interval delta t becomes infinitesimally small. So in only which is the thing which is written here is just mathematically written as nothing but what is v? V is nothing but equal to, we already know it is delta x by delta t. But as we need to say that delta t is very zero, the mathematical form to write it as limit delta t tending to 0. So that is how we explain this situation. When you will go with further in your differential calculus concepts, you will understand two different approaches. One is called as differentiation, one is called as integration. Okay, so basically this terminology here can also be written as equal to dx by dt. Okay, so let's not go into the mathematics part of it. That will be understood to you very clearly when you will understand differentiation, limits, etc. So right now, just to explain to you what does this d stand for. So this is nothing but differential. So we are doing the differentiation of x with respect to t. So this is, let me just keep on writing also so that you can understand. That is nothing but differentiation of. Okay, so that is the basic mathematical analogy which has been explained here. So hope I was able to explain to you this. Let's move on with the further concepts here. So where the symbol, so it is just explained there, where the symbol limit delta t tending to 0 stands for the operation of taking limit as delta t tending to 0 of the quantity on its right. So this delta is already been explained to you. So this delta is basically a Greek letter which just tells you you need to do the differentiation of any concept which is written just about it, that is final minus initial. Not the differentiation, sorry, the difference of it. Okay, every word has equal importance, every word is different here. So it's nothing but difference of the final value minus initial value. Whatever the thing is written here, final value of that minus initial value of that. Okay, right. So in the language of calculus, the quantity on the right hand side of the equation, first equation, is the differential coefficient of x. That's differential coefficient of x with respect to t, and is denoted by dx by dt. Okay, so it's also called as dx by dt, or the differential coefficient of x with respect to t. Okay, so we can use the first equation So we can use the first equation for obtaining the value of velocity at an instant, either graphically or numerically. So we will understand how to do these things, and the examples comes in our slides. Okay. So let's begin with the next discussion now. So suppose that we want to obtain graphically the value of velocity at time t is equal to 4 seconds. That is point P. So this is the point P for the motion of the car represented in the left figure. So let us say that this was a graph given to us, and we need to find out what was the value of velocity at time t is equal to 4 seconds. Okay, please remember this is the position time graph. On the position time graph, even if you draw the graphs like this and like this, you won't get the value of velocity, right? If this would have been, let us say, v, and this would have been t, then we would have gone to 4 seconds and we would have found out the velocity. But that is not the case here. So how to do that is the explanation being explained. Okay, so the figure has been redrawn in right, choosing different scales to facilitate the calculation. So it just has been magnified here. So now let us understand the situation. Okay, so let us first take delta t is equal to 2 seconds centered at t is equal to 4 seconds. So now the complete example of this complete methodology which we will try to understand here is just to make you understand the basic crux of why we are trying to reduce the value of time interval. Okay, so that just the explanation which I just give you on the black screen, in which we are trying to decrease the value of delta t, will be understood in much more clarity in this example here. Okay, so this is basically the graphical example, but after this we will understand that every time we cannot use the graphical results for all of these examples, the future examples, and hence we should understand differential calculus and the numerical part. Okay, so here we'll try to use the graphical methodology, and then afterwards we will understand the numerical methodology of it also. Okay. Fine. So let us take delta t is equal to 2 seconds, centered at 4 seconds. So if it is centered at 4 seconds, that means you are taking delta t by 2 at this direction, delta t by 2 at this direction. Okay, let us try to understand this clearly. Okay. So then with the definition of average velocity, the slope of the line P1, P2 gives the value of average velocity over the interval 3 to 5 seconds. Okay. So if delta t is 2 seconds, that means we are going 1 second from here, so it will be 3, and 1 second from here to 5. So basically we are trying to find out the displacements at this value and this value, and then we are just doing x2 minus x1 upon t2 minus t. Okay. Now we decrease the value of delta t from 2 to 1 second. So now what is happening this time? This time as delta t is 2 to 1 second, so therefore 4, we will go this time 3.5 and this time 4.5. So that delta t is 1 second. Okay, so this time here it is, we are going 3.5, here we are going 4.5. Again, it is nothing but x2 minus x1. So we know the value of x2 here, we know the value of x1 here. So we are just trying to find out x2 minus x1 upon t2 minus t1. That being said, next thing is, so then line P1, P2 becomes Q1, Q2, and its slope gives the value of the average velocity over the interval 3.5 seconds to 4.5 seconds. Next, in the limit delta t tending to 0, the line P1, P2 becomes tangent to the position time curve of the point P. I think you know the meaning of tangent to the point curve. So basically, let us say this is the curve, and we say that a line is tangent to this position. So this basically means that if you try to make a line which is normal to the curve, and this would be perpendicular to it. Okay, or there will be a single point which is directly passing through this tangent. Okay, so that is the basic definition of tangent. You'll understand a tangents concept much more clearly in the mathematics, then you will understand circles, etc. So let's look over that in the future positions. Let us try to understand the concept here first of all. So the limit delta t tending to 0, the line P1, P2 becomes tangent to the position time curve at the point P, and the velocity at t is equal to 4 seconds is given with the slope of the tangent at that point. Okay, so slope of the tangent is, I also explained the concept of slope again. So this is basically the slope of that line. Fine. So next thing is it is difficult to show this process graphically, but if we use numerical method to obtain the point value of the velocity, the meaning of the limiting process becomes clear. Okay. So let us try one numerical methodology and try to understand this. Okay. So for the graph shown in the figure, this is how we can define the graph in the equation form. So that is x is nothing but equal to 0.08 t cube. Okay. So table below, as you can see, there's a table below. It gives the value of delta x upon delta t calculated for delta t equal to 2 seconds, 1 seconds, zero point 0.5 seconds, 0.1 seconds, 0.01 seconds, centered at t is equal to 4 seconds. Okay, so what we are doing, we are just trying to decrease the value of delta t here. Let us try to decrease. So just keep on seeing the table also, and I will try to iterate also. So as you can see, first value is delta t. It's 2 second, 1 second, 0.5, 0.1, 0.01. Okay, so as example, let's say we need to find out the value at 4. What you will do, what you will do, let's say it's 2 seconds. So we will do delta t by 2 and then subtract 1 first side and then add 1 first side. So it will be 4 minus delta t by 2 in this direction, and then this time it will be delta 4 plus delta t by 2, which will be 5 in this direction. So we will go from 3 to 5. So what we are basically doing, let us say we have some t, we had delta t, we divided it by 2, and then what we did was we had the range of t minus delta t by 2 to calculate the value of displacement at this position, and similarly we have t plus delta t by 2. Okay, so that was the range of your procedure. That was the range which we used for the procedure of calculation of your instantaneous velocity. Okay. So that thing is also written here. So the second and third column gives the value of t1, that is t minus delta t by 2, and t plus delta t by 2. And the fourth and fifth column gives the corresponding values of x, that is x of t1 is nothing but, so now as you know the value of t1 because it is on the graph, so that values can be explained or equated from this equation here. Using this equation, we are just putting the value of t1 here, then we are putting the value of t2 here, and then finding out the value of x1, and then similarly x2. Okay, so as you can see, t1 has been explained. T1 is nothing but this. Similarly, t2 has been explained. T2 is nothing but this, depending on your delta t values. Okay, t value is 4 seconds used here. Okay, similarly we got x of t1, so just putting the value, let us say for the first it is 0.08 into 3 cube, for the second it was 0.08 into 3.5 cube, etc. Similarly x of t2, so you use this values here, this values here. Finally, after this calculation, what you did was you calculated the value of x of t2 minus x of t1, which gave you the value of delta x. And now you know the value of delta t, you know the value of delta x, you just calculate the value of delta x upon delta t. Okay, so that was a numerical methodology which we adopted for calculation of instantaneous velocity. Okay, so the second and third columns gives the values of t1 is equal to t minus delta t by 2 and t plus delta t by 2, and the fourth and fifth columns gives the corresponding values of x, that is x of t1 is equal to 0.08 t1 cube and x of t2 is equal to 0.08 t2 cube. Okay. The sixth column lists the difference delta x is equal to x of t2 minus x of t1, and the last column gives the ratio of delta x and delta t, that is the average velocity corresponding to the value of delta t listed in the column. So that was how this thing is explained. Moving on, so we see from table that as we decrease the value of delta t, the value of the average velocity approaches the limiting value. So as you can see, as we're trying to decrease, this value is converging to the location, or sorry, not come to the location, it is converging to the value of 3.84. Okay, so that is the thing which we need to understand here. So the average velocity approaches the limiting value of 3.81 meter per second, which is the value of velocity at t is equal to 4 seconds. That is the value of dx by dt is nothing but equal to t is equal to 4 seconds. Okay, so even if you try to find out the value of dx by dt for it, or if you try to calculate the value of dx by dt for it, and then put the value of t is equal to 4 seconds there, you will get the answer as equal to your 3.84 meter per second. Okay, so for this case, the variation of velocity with the time is found to be shown in the figure below. Okay, so what you basically just did, either you can go with this method, but this is very tedious method. If we can just calculate the value of dx by dt, you will get the value as a function of t. Just try to plot the graph of that, and this is how you will get the graph. Okay, so for this case, the variation of velocity with time is found to be as shown in the figure below. Okay, fine, let's move on. So the graphical method for the determination of the instantaneous velocity is always not a convenient method. We just understood this thing. Why? Because you can see the amount of calculation which we did for just finding out the value of instantaneous velocity at t is equal to 4 seconds. What about all the infinite points which are present between t is equal to 0, 10 seconds, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then the 0.5 locations, then 0.50, 0.51, 0.52. So there are several points for which instantaneous velocity can be calculated, and every time we cannot do this graphical method or this numerical method. Okay, so the graphical method for the determination of the instantaneous velocity is not always the convenient method. So for this, we must carefully plot the position time graph and calculate the value of average velocity as delta t becomes smaller and smaller. It is easier to calculate the value of velocity at different instants if we have data of positions at different instants or exact expressions for the position as a function of time. So this is the methodology which we adopt generally. Then we calculate the value of delta x by delta t from data for decreasing the value of delta t and find the limiting values as we have done in table 3.1, or use differential calculus for the given expression and calculate dx by dt, the thing which I was trying to explain to you, at different instants as in the following example. So let us understand the next example, and then this will be clear as to how the differential calculus is being used. Okay. Okay, so first of all, read the example and the question, and then we can move on to the understanding the differential calculus here. Okay, so the position of an object moving along x-axis is given by x is equal to a plus bt square. Okay, so we have x is nothing but equal to a plus bt square. So what you can understand, that as the value of t increases, the value of x increases. As the value of t increases more, the value of x increases more. You can see a and b are constant values. Okay, a value is given to you as 8.5, b value is given as 2.5. Let us try to write that equation directly. So then x is equal to nothing but 8.5 plus 2.5 t square. Okay, and t is measured in seconds. Okay, so if t is 1, so x is nothing but 8.5 plus 2.5. If t is 2, then it is 8.5 plus 2.5 times 4. Okay, the question asks is just you need to calculate the velocity at t is equal to 0 seconds, at t is equal to 2 seconds. What is the average velocity between t is equal to 2 and 4 seconds? Okay, so there are two different concepts. If I calculate the velocity at t is equal to 0 and t is equal to 2, it is nothing but your instantaneous velocity being asked. Okay, so first of all, please remember that d by dt of a constant value is 0. Second thing is d by dt of let's say x to the power, or not x to the power, will come here, d by dt of t to the power, let's say n can be any quantity, is n times t to the power n minus 1. For example, d by dt of t square will be 2 into t to the power 2 minus 1, which is 2 into t. Okay, so for this question, we need these two differentiation rules. So just understand these rules for now, and then we can go with further discussion. Okay, so therefore in notation of differential calculus, the velocity is what? So the velocity is nothing but v is equal to dx upon dt, that is d by dt of a plus bt square. So let's try to find out that value here. So it's d by dt of a plus bt square. So we can just differentiate, we can just separate both of them here. So it is nothing but d by dt of A plus d by dt of bt square. So this is one of the property of differentiation. You can separate them if they are several different quantities. So we just understood that for constant it is 0. So this will be 0 plus d by dt. This can be again said as equal to b times, as b is a constant, we can keep it out on the differentiation of t square, and hence this will be nothing but equal to 0 plus b times. You understood right now that d by dt of t square is nothing but 2t. So we are just writing this as 2t. This is equal to 2bt. Okay. So just keep on practicing differential calculus, because this is very important concept in the physics and mathematics portions. Okay. So finally what we got is that velocity is nothing but equal to 2pt. What is the value of b given? B is given as 2.5. So we'll write this as equal to 2 into 2.5 into t. Therefore velocity is equal to nothing but 5t. Okay. So as you keep on increasing the value of t, you will get different values of velocities. Okay. Fine. So dx by dt has been explained. So finally what we got is dx by dt is nothing but equal to 5t meter per second. So at t is equal to 0, just put the value of t 0 here. You will get the velocity as equal to 0 meter per second. Put the value of t is equal to 2 here. You will get 5 into 2, that is 10 meter per second. Okay. Now let us calculate the value of average velocity. We know the formula for average velocity. What is average velocity? Average velocity is nothing but x2 minus x1 upon t2 minus t1. How to calculate the value of x2? So just put the value of x of x2 basically t at 4 seconds. Okay. So it is nothing but your a plus b into 4 squared minus a plus b into 2 squared, because it is this is the final value, this is the initial value, divided by 4 minus 2. Right? So quite clear. A and A can get cancelled directly. Right? This would be nothing but b times 16 minus 4 divided by 2. So it is 16 minus 4 will give you 12, and this will be nothing but equal to 2.5 multiplied by 12 by 2. So this is nothing but this. This will give you an answer as equal to 15 meter per second. Okay. That is nothing but 6 into 2.5, which will give you the answer as equal to 15 meter per second. Okay. Therefore, the average velocity is 15 meter per second. But as you can see so that were all the questions which were being asked here. So first answer is your 0 meter per second. Second answer is your 10 meter per second. And the final third answer is your 15 meter per second. Okay. So from last figure on velocity time graph corresponding to motion, we know that during the period t is equal to 10 to 18 seconds, the velocity is constant. So the question is completed. Now we are just having another discussion. You can see from t is equal to 10 to 18 seconds, here the velocity is constant, right? From t is equal to 10 to t is equal to 18. So from the last figure on the velocity time graph corresponding to motion, we know that during the period t is equal to 10 to 18 seconds, the velocity is constant. Between period t is equal to 18 to 20 seconds, it is uniformly decreasing, and during the motion t is equal to 0 to 10 seconds, it is increasing. So as you can see, it is decreasing uniformly here, and it is increasing here. That is being explained there. So note that for uniform motion, velocity is the same as the average velocity at all distances. Okay. So velocity, so basically velocity is instantaneous velocity. Okay. So only and only for uniform motion. Okay. Please remember, only for uniform motion. Okay. What uniform motion basically? Uniform motion is when the amount of displacement covered is same for equal amount of time interval, any time interval which we take. Let us say we take delta t is 2 seconds. So for every 2 seconds, if delta x is coming out to be, let's say 5 meters, and that motion is called as a uniform motion. So it's just a note that for uniform motion, the velocity is the same as the average velocity at all instants. Okay, so that was the explanation being done here, that velocity is instantaneous velocity will be same as the average velocity at all instants. Okay, fine. So let us end this discussion here only. From the next lecture, we will start with this discussion, and then we can move to the new subtopic, that is acceleration. Okay, so let us end the topic here. So in this lecture, we are currently on the fourth topic, that is instantaneous velocity and x speed. And after this, only last few points are few discussion, 5 6 points are remaining, and then we can move on to new concept, that is acceleration. After acceleration is done, the main concept is understanding the kinematics equation for uniform motion, accelerated motion, and then we can finally move to relative velocity, and that will be the end of your motion in a straight line. Okay, so that's it from this lecture. So thank you so much.